wreak havoc on the average. But nonetheless, it's got to be accounted for. Is that recording? It is. Okay, good. 26. 26. 1, 2, 3. 3. 27. 28. Love this. 29. 30. There we go. 31. 32. There we go. 33.
No. 34.
34. Okay, so we'll do this and we'll do this. Thank you, Michelle. Oops, not 10. All right. 35.
Wait, we have a 34.
Wait, hang on. We have a 34. That's okay. That's okay. I'm sorry. And you have a 34 as well, Simi? Okay, 3. And then, Des,
I had a 34.
You have a 34 as well? Sorry. Cool little hiccup there. Little stegosaurus tail. Let me move this so I can see you guys better. There we go. And we have a 35. Got one of those. Love this. 36. Uno. 37. Oh, you had a 36 as well, Michelle?
Never mind.
Never mind.
Nope.
37. 38. 39. 40. Okay, who's above 40? Let me hear him. 45, Aaron. 45's down here. There's a 1 there. Who else? Oh, that's it. We got off easy today. Oh, nice. We got off easy. There it is. Holy hell. Look at that graph. Freaking gorgeous. Where's the average? Blood pressure. Here we go.
12.1.
Well, I got good answers. Now, what I'm going to do is I'm going to do the blood pressure thing. Or the, blood pressure. We're going to do systolic, diastolic. Here we go.
Stop.
Okay. That's where your guys' guesses were. All between there and there. So it looks like between like 12 and about 17. Cool? Now, as it turns out, the average is, if I remember correctly, which I don't, I'll calculate it for you real quick. You can do this in one of our stats, but it's a tad bit obnoxious. So I'm going to do equals this times, times this. We're going to drag this down. Okay, and then we're going to add all that up. That divided by that. $14.6. You guys caught the average. Because it was between 12 and 17. Well done. Well done. Your average is right about there. Right about, ooh, damn it. Right about there. Kind of cool, huh? Now, if you needed to, you could do that in TI, of course, right? You could do L1, L2. It's a little bit tedious with the number of numbers. But let me show you something that's kind of cool. What I did was I replicated your experiment. You guys are the red that's in the front there. The green curve behind that is what should have happened theoretically if your coins or your dice fell exactly perfectly. Now here's what that curve looks like. I want to select you guys' data. Hang on. There. That's what the perfect theoretical curve looks like. And its average, if I remember correctly, is closer to like 13 or 14, right about there. Yours is a little bit further past. That's because your tail was a little bit heavier. You had those hiccups at 35 and 36. There shouldn't be hiccups over an infinite length of time, right? Over an infinite length of time, you shouldn't have those those spiky cookies on the tray. The tray should actually do this and then slide off. Isn't that badass? It's called a gamma curve. It's very, very cool statistics. We'll study that in 243. Totally lopsided. Take a bell curve and smush it on one side, and it pops over to this side.
Tidal wave.
It's like a tidal wave, exactly. A wave curve. Very nice. So much in statistics is governed by this. The chickens and the roosters, for example, in a large flock. Or the number of A's, B's, C's, and D's on a multiple choice exam that's randomized properly follow these curves too. Very, very, very cool curves. But you guys, your results, look how close they were. I mean, you only did a couple hundred results, and you got damn close to what it should have been. Pretty sweet, huh? I did the same thing for the first experiment we did today. Okay? That's the theoretical. That's what should have happened perfectly theoretically. Perfectly theoretically. And here's what you guys got. Hot damn, it's not that far off. It really isn't that far off. Of interesting note, it should take exactly the same probability to get 3 as to get 4. You guys had a fun little spike at 4 where you shouldn't have been, but that's okay, because the 3s would have caught up eventually. They would have caught up eventually if we played the game enough. Which you will on the quiz next week if you want to do the quiz for next week, which I haven't posted yet. I'll post it later. Good so far? Now, there is a neat connection. This whole problem started with me and my son, and I'm going to tell you more about that. There's a problem, and I wasn't considering even putting this in Math 105. It's called the coupon collector problem. If you have, you guys remember, maybe you still do it. Maybe, I don't even know if cereals do this anymore. Cereals used to put little prizes in the cereal. You know, you collect all 12, or collect all 8, or one of those things, right? And you go to the store, and you buy them. And they still do it!
I got one.
Yay! That makes me so a happy little present, right? A Happy Meal. Happy Meal, same thing, right? They got a new movie comes out, they make all the characters little tiny figurines. Collect all 4, and meanwhile your blood pressure's going through the roof because you're eating McDonald's food all the time. But there's a fun little mathematical problem called the coupon collector problem. And what it says is, on average, how many coupons do you have to collect until you're reasonably sure you've got at least one of each? So how many boxes of cereal do you have to buy if you want the entire set of what's in the cereal? How many boxes of cereal would you have to buy until you're reasonably sure you've bought all the little tiny prizes? And what's neat is, I'm going to take that line off. What's neat about it is, that's the pattern in the scatter plot that's shown right there, friends. Now that looks almost linear, doesn't it? It's not, but it's almost linear. You could argue that that's linear behavior. So if you have 6 coupons, it's going to take roughly 14 tries to get at least one of each of those 6. You guys just did that experiment, didn't you? That's the experiment you guys just did. You averaged 14 point, whatever it was, 14.6? 6 coupons. 4 sides of a coin. Right? 4 cards, 4 suits in a deck. 2 sides of a coin. The Star Wars, it doesn't go out far enough to see it, but the Star Wars, one of my favorite questions is, how many eBay sales would you have to make it reasonably sure you've got one of each of the 1977 collectible Star Wars trading cards, of which there are like 69 cards. It ends up being hundreds of cards you have to keep buying in order to have them all. Why do I tell you this? Because it happened with my son. It happened with my son at Legoland about 2 years ago. Now, huge Lego fan. I don't know if you guys are too. Huge Lego fan. So, say that again?
Legos are awesome.
I think so too. I think so too. One of my favorite toys, and he's in love with them just like I am. Lego Movie, one of the greatest experiences for both of us ever. So we're in Legoland, leaving, and he walks into the store. He's like, "Hey, look, Dad, they sell minifigures in little bags," which is a new thing they started doing, I guess, a few years ago. It's been a while now, I guess. I didn't notice it until 2 years ago. So a minifigure is one of the little people, a little punk rocker with the mohawk, and a little skater, right, little hockey player, little princess, and they're in little bags, and they release them in sets. And they're in sets of 12. Each release is 12 different minifigures, and they put one in each bag. And he's like, "Dad, there are 12 of them." I'm like, "Heck yeah!" And he's like, I want to get all of them." And he walks up and grabs 12 bags, and he puts them on the. And I laugh, and I'm like, "That's pretty cute, dude." He's like, "I got my own money." I'm like, "I know, but do you think you got them all in there?" He's like, "Well, there's 12." It's like, "Yeah, there are. There's 12." And he's like, "And I bought 12 bags." And I'm like, "Yup." And the whole time I'm going, Math 105. This exists because of that discussion I had with him. And I stopped it there, because he was 5. And there's no way in hell he would have understood that at that age. Now since then, interestingly enough, he started flipping coins as a fun game with me because I've already poisoned him. He flips coins now with me. He's like, "Bet, Dad, bet." He's already figured out that if I always pick tails, I win half the time. No matter what he flips. He's figured that out. I never told him. I just always pick tails. "Daddy, why do you always pick tails?" I'm like, I'll tell you someday. And finally, he figured it out after about 6 months of doing that. You win half the time. Mm-hmm. So he's already got an idea of what 50% means, right? So what I have an idea about is that 10, 11, 12, he would have had to buy closer to 38 bags in order to reasonably be sure he's got one of each. What I'll have you guys do for your quiz for next week is actually run that experiment and collect that data to get that number. You probably won't get exactly 38, I'm guessing, but you'll get around it, just like you did in class with our coin flips back and forth. Make sense? And then you do realize how you can use your TI program to do that, yes? It's a what-sided coin for the Legos?
Well,
12-sided coin. It's a 12-sided coin, which is not the same as rolling 2 6-sided coins, believe it or not. And we'll study that in this class, starting next week. Not right now, though. Make sense? Pretty sweet, I think. Pretty sweet. So that's the beginnings of randomness, and I think it's one of the neatest. The past week of discussion is all because of Max standing in Legoland, and my brain just going like, this is so damn cool. This is so damn cool. How can we apply this? But it teaches you guys how to at least recognize when something is being random or not. At least recognize. If he had bought 12 bags and got one of each, I would have keeled over. Because the chance of it happening is basically 0. The chance of you rolling a die and getting one of each of the sides in the first 6 rolls is 1.5%. It's going to be exponentially squared smaller to happen with 12. It's going to be that squared, which is 1 in 100,000. I mean, it shouldn't happen. Fair enough? Good.